Suppose we have lots of multiplications. Suppose you have to do not one multiplication, but you are dealing in a digital signal processing environment where you have to do millions and millions and millions of multiplications. You're taking in a stream of audio and you're slowly converting it into MP3, and that involves, polytone filters and FFTs, and you have a lot of multiplications you need to do. Can we do better from a cost performance standpoint? In other words, can we, for instance, either get better performance? Can I, rather than having to wait, getting a throughput of 1 over n, can I get better throughput? Another thing is maybe I can use less hardware. So those are the things we're going to think about. Okay, so we know how to do pipelining. Okay, so your next task is remembering our lecture on pipelining, and just think of this now as an abstract electrical circuit. Forget the fact that this is really doing multiplication. Just think about how I would draw my arcs across this diagram to break it into something that would have better throughput. So here's attempt 1. Thoughtfully labeled stupid pipeline tricks, because it's probably not our best choice. If I think about pipelining, this is a perfectly legitimate pipeline. The arcs are going, all the way across, from one side to the other, going across all the outputs, and so this is all fine. Okay, what is the latency and throughput of that pipeline circuit? Well, there's n pipeline stages, because I basically broke each one of the n rows here into a separate pipeline stage. The clock period is order n, because remember, I have to get the carry chain all the way across this whole set of additions. And remember, there's a carry out from this guy that becomes the carry in here. So the long path here comes in at the low order block, and then the carries have to propagate all the way through. And the longest such row is 2n. So we have basically order n TPD for in the worst case, for the row that takes the longest time. So that means that the clock period is order n. We still have n squared hardware. Think of this as really just adding 2 registers to each of these blocks, or just registers on these two output bits. And so that means I've gone from a hardware cost of 2 full adders and an AND gate. I've just added a little, that constant is now a little bigger, but it's still a constant cost. So given that I have n squared blocks, I have order n squared hardware. The latency is n times the clock period. I have n pipe stages times a clock period of n gives me an n squared latency, and a throughput then of 1 over n, because I get one answer every clock period, and the clock period is order n. So I've done a lot of pipelining, but I actually haven't changed anything. The hardware cost is the same, or at least in order of notation. I've sort of added a lot of registers, but in terms of order of, I've not made the hardware cost any different. But I haven't achieved anything either I've made the latency longer. The latency is now n squared instead of order n, but I haven't achieved better throughput. So this is, you can say, oh, that was pipelining, but it didn't get the job done. And the problem is this order n cost in each pipeline stage. I know, I'll break the carry chain this way. Here's my picture carefully showing a bunch of arcs. Well, this is just stupid, okay? This is, I love this word, stupider. This is not a well-formed pipeline at all. I love him. Such a jerk, Okay, so here's a path through the circuitry, the sort of sum bits in this column, in which it sees no registers, and the next one sees umpteen registers. This is just not a K pipeline. So it is possible to draw lots of arcs, but we have to remember to be good about drawing arcs that actually get the job done. Hi, Mom, I'm in lecture. Could I call you back later? Okay. Okay, so what we're going to do is we're going to pull the diagram apart in a slightly different way. And what you can see is I've sort of split the diagram apart along the diagonals, taking into account the fact that, remember I had how information sort of flows down and to the left? Well, what I've done is I've exposed the down and to the left arcs. And in some ways so this arc here, which usually just went to the left, is now down and to the left. So this is exactly the same picture. I've just stretched some of the wires. And now what I'm going to do is to start drawing pipeline stages like so. And a miracle has happened. Okay? Think about the latency and throughput of this circuit. Okay, and we're going to show the sticker on the next page, the EPA sticker for this circuit on the next page. But this circuit has remarkably different performance characteristics than anything we've shown so far. Okay, so what is the clock period that I have to use? Okay, and what clock period can I use to clock the pipeline registers here? In other words, what's the longest combinational path from one of these registers to an output register? Well, you think a little bit, right? We have bits that are coming in, okay, and there's a path, okay, that goes from one side to the other, but the longest path is basically constant. In other words, as I make the number of operands, if I make n bigger and bigger and bigger, these diagonals get bigger and bigger and bigger, right? But I split things along the diagonals, so everything grows this way, and I add more pipe stages, but there's sort of constant time here. So this is the clock period here is constant. It doesn't, as I change the size, if I go from 32-bit multiplications to 64-bit multiplications, I don't have to use more hardware. Okay, and it will take me more cycles of latency to get the answer, but I won't have to change the clock period. So there's sort of a constant path here that's independent of the size of the operands. Okay, so we have order n stages. So if I doubled the size of the operand, I would have, more arcs I would have to draw, roughly linear growth there. The clock period is constant. Okay, it doesn't grow as n at all. The hardware cost is still n squared. I haven't changed the hardware cost at all. The latency is now n times 1, so I'm back to the original latency of my combinational circuit, which is good because you sort of like to say, can I make things work better without making the latency longer if I can? So that's achieved here. And when I'm all done, what I discover is I have throughput. I get one answer every clock period. So even though I can make the multiplication bigger and bigger and bigger, I'm getting one answer every clock period, and the clock period is constant, independent of the operands. So this sticker here, okay, for about the same hardware cost and latency, has throughput that's n times better, this pipeline multiplier. Okay, and the way in which we just structured the problem made it easy to see the pipelining we needed to do to achieve a clock period that did not grow as n. So that's the sort of the purpose of our big exercise. Suppose we said, okay, I'm much more interested in size than I am in throughput. Right? So if you think about our big problem here, is there a way I can think about this pipeline multiplier and say, well, I sort of like it, but I only have a multiplication to do once in a while. Is there a way I can restructure this to somehow get a hardware multiplier that costs much less than n squared? Well, let's think about our problem. So, here we have one diagonal that's busy computing A0 times all the B bits, and this diagonal is computing A1 times all the B bit and taking the result from the previous diagonal and putting it together, and so forth and so on. Think about how does the problem differ as I go from diagonal to diagonal to diagonal? Well, hardware-wise, it's exactly the same picture, right? I'm just feeding it sort of different generations of data bits, right? I'm taking the results from the previous diagonal and putting in a new A bit and piping along the B bits, but I'm really sort of reusing this one little diagonal stripe again and again and again, and my naive implementation had n copies of that stripe. But suppose I reorganize it slightly and say, look, what I'm going to do is to take one copy of the stripe hardware and reuse it n times. Right? So this is how I'm going to get my hardware savings. Right? Look at the cost now. So we have a one-stage pipeline, if you will. We actually have to run it through n cycles. So the latency is still order n. We have to run it n times. But the hardware cost is now dramatically lower. Right? It grows as the size of the operands. It grows as the size of one of these stripes. So here's another EPA sticker, that's on a different model in the showroom that actually has a much dramatically lower hardware cost. I mean, we went from n squared down to n. Okay, and what I've done is to actually allow myself now to reuse my stripe in a way that gets me the same answer, I'm going to take longer to do it. In other words, the throughput now is back to 1 over n, which was the throughput of our combinational circuit. Okay, but the hardware cost is now dramatically lower. Sort of neat, right? We've been able to trade off. We took the fancy pipeline multiplier, which had tremendous throughput, and said, I'm going to trade off some of the throughput for lower hardware cost.